Hello everyone, welcome to Alchemistry. Hope all of you are doing well. In my previous lectures, I have discussed what is VBT theory and how the hybridization of the central metal atom of complex compound is determined. In this lecture, I am going to discuss about the geometry and shape of the complex compound. When the central metal atom is hybridized, then the hybridized orbitals are arranged in the three-dimensional area around the central metal atom in a particular fashion, and thus the complex compound achieve a particular shape or geometry. If the central metal atom is sp3 hybridized, if it is sp3 hybridized, then the shape of the complex compound becomes tetrahedral. A tetrahedral shape looks like this. In this shape, you can see this is the central metal atom, and all the ligands attached with this central metal atom will be at the four corners of this tetrahedron. If the central metal atom is gsp2 hybridized, then it gets square planar geometry or square planar shape. Where the central metal atom is placed at the center of this square, and all the four ligands are placed at the four corners of this square, right? But if the central metal atom is sp3 d2 hybridized or d2 sp3 hybridized, then the complex compound becomes octahedral. An octahedral structure looks like this, where a square is placed and central metal atom remains at the center of a square. A ligand possesses ava position and another ligand remains at the bottom or below the plane, and the rest of the four ligands are placed at the four corners of the square, right? So this is the octahedral geometry. Here you can see this is the central metal atom, and all the four ligands are attached at the four corners of the square. I have taken some example to discuss the different type of hybridization of the central metal atom and their geometry. Here you can see this is square bracket, this is the ligand Cl minus, this is the ligand, and this ligand is attached with this central metal atom. This is the central metal atom, right? We know copper is 3D series transition metal. Among the different 3D series transition metals, copper has 3D9 electronic configuration. If I open this 3D9 electronic configuration like this, 1, 2, 3 and 4, this is 3D, this is 4s and this is 4p. Copper has 3D9 electronic configuration. That means this 3D orbital contains 9 electrons. 1, 2, 3, 4, 5, 6, 7, 8 and 9. When 4 Cl minus ligands comes to bind with this Cu2 plus, this Cu2 plus ion, then the 4 Cl minus donate its lone pair of electron to 1 4s and 3 4p like this. They donate their electron like this. because here 3d orbital is not vacant. All the orbitals of 3d subshell are occupied, so there is no vacant d orbital, 3d orbital here. So Cl minus puts its electron in the vacant 4s orbital and in the 3 4p orbital. Here you can see that the central metal atom has utilized 4s and 3 4p orbital for hybridization before bonding with Cl minus. So the hybridization of the central metal atom becomes sp3. As the central metal atom has obtained sp3 hybridization, so its geometry becomes tetrahedral, where the central metal atom copper remains at the center of the tetrahedron and all the 4 Cl minus ligand remains at the 4 corners of the tetrahedron, right? Like this. Like this. And this becomes the shape of the CuCl4. All the ligands are Cl minus, so the ligands will be Cl minus here. You may have a question that how I have written this 2 plus. I have calculated the oxidation state of the central metal atom, and the oxidation state of central metal atom copper becomes 2 plus. For that, I have assumed that the oxidation state of central metal atom copper is X plus there are 4 Cl and each Cl is minus 1, so overall charge is minus 2, and that's why X becomes plus 2. This is how I have calculated the oxidation state of central metal atom, and from this calculation I have known the hybridization of the central metal atom, and the hybridization of the central metal atom is sp3, so it becomes tetrahedral. CuCl4 2 minus, this ion, this complex ion have tetrahedral geometry or shape, right? The next example is Zn NH3 whole 4 2 plus. Here you can see this is the square bracket and NH3 is monodentate ligand. This is neutral monodentate ligand. As it is neutral, so its charge is 0, and zinc is metal and it is central metal atom. To know its oxidation state, let us take its oxidation state is X, then 4 into 0 is equal to plus 2. This is overall charge and X becomes plus 2. That means the central metal atom zinc is plus 2 oxidation state, is in plus 2 oxidation state. Zinc when becomes plus 2, it has 3d10 electronic configuration. If I open this 3d10 electronic configuration, then it becomes like this. All the d orbitals, all the 3d orbitals are completely filled here. 4s orbital is empty, and all the 4p orbitals are empty here. When 4nh3 comes, to bind with Zn2 plus, then it donates its electron, lone pair of electron, to 1 4s orbital and 3 4p orbital. Like this. So the central metal atom has utilized 1 4s orbital and 3 4p orbital for bonding. So the hybridization becomes sp3. So the central metal atom is sp3 hybridized, and the complex compound or the complex ion here attains tetrahedral geometry or tetrahedral shape, right? At the center of this tetrahedron, zinc remains, and its four corners are occupied by four NH3, like this. Obviously, this bonding is coordinate bond because the lone pair of electron on nitrogen atom is donated through coordinate bond to the central metal atom zinc. Overall, the charge is +2. So this is the tetrahedral geometry of Zn NH3 whole 4 2 plus. Next example is PtCN whole 4 2 minus. Here you can see this is square bracket, this is ligand, Cn is ligand, and its charge is -1. Central metal atom is platinum. So if I assume that the oxidation state of the central metal atom is X, then X plus 4 into -1 is equal to -2. That means the oxidation state of the central metal atom becomes +2. Platinum, when becomes +2 oxidation state, its valence shell electronic configuration contains 5d8 electronic configuration. So if I open this 5d8 electronic configuration, it becomes like this, 5d8, and all the 8 electrons remains like this. Only 2 unpaired electrons here. This is 4s orbital and this is 4p orbital. When 4Cn- comes to bind with the central metal atom, that means Pt plus 2, then the 5d orbitals first rearrange its electron to accommodate the incoming Cn-. To accommodate the incoming Cn-, this electron now comes to this orbital to vacant this orbital. That means one of the 5 orbitals of 5d subshell now becomes vacant to accommodate the incoming Cn-. Already 4s and 4p orbitals are vacant. So incoming Cn-, you can see there are 4 incoming Cn-, and one of the 4 incoming Cn- donates its electron to 5d orbital. One of the 4 incoming Cn- donates its electron to 4s orbital. So for bonding, one 5d orbital has been used and one 4s orbital has been used and two 4p orbital has been used. So the hybridization becomes dsp2. As the central metal atom is dsp2 hybridized, so the complex becomes square planar. Its geometry becomes square planar. And it looks like this. This is a square plane. Central position is occupied by central metal atom, that is platinum. And all the 4 ligands are attached with the 4 corners of this square plane. Overall charge is -2. Okay, so this is becomes square planar. Next example is this one. This is square bracket, you all know, and this is ligand. This is also a ligand, but there is a little difference between the two ligands. This is monodentate ligand and this is neutral monodentate ligand, so its charge is 0. This is bidentate ligand and it has -2 charge because it is oxalato, right? This is central metal atom, Let the oxidation state of the central metal atom is X plus 2 into minus 2, and there are two H2O, so 2 into 0 is equal to minus 2. So X minus 4 is equal to minus 2. So oxidation state of the central metal atom becomes 2. That means nickel becomes plus 2 oxidation state. So its electronic configuration becomes 3d8. If I open this 3d8 electronic configuration, so it becomes like this: 1, 2, 3 and 4. This is 3d8 and this is 4s, this is 4p, right? And this is 4d, 1, 2, 3 and 4. The 4 ligands, when comes to the central metal atom to bind with, then you can see 3d orbitals are occupied, though there are two unpaired electrons here, but the ligands don't come to the inside 3d orbitals. Rather, they donate their electrons to 4s orbitals, 3 4p orbitals, and 2 4d orbitals, like this. You can see there are 6 ligands there. All the 6 ligands donates their lone pair of electrons to the 4s orbitals, 4p orbitals, and 4d orbitals. One 4s orbital, 3 4p orbitals, and 2 4d orbitals has been used. So the hybridization becomes sp3d2, and the geometry or shape of this complex part of complex compound becomes octahedral. And the octahedral structure of this complex compound becomes like this, where nickel remains at the center of this square plane, and above this plane there are one ligand. I am putting H2O, and below this plane there is another ligand. These two bonds are coordinate bonds because H2O is neutral and lone pair of electrons on oxygen atom has been donated to the central metal atom via this coordinate bond. This square plane contains the central metal atom nickel, and at the four corners of the square plane the two oxalato ligands are attached. This is oxalato, so oxalato is attached with the four corners of the square plane. Overall charge is -2. So this is octahedral geometry or shape of this complex compound. Next example is this one. This is square bracket, and these all are ligands. This is monodentate ligand, neutral, so its charge is 0. This is bidentate ligand, ethylene diamine, so its charge is 0. This is neutral. This is monodentate ligand, but it is negatively charged, and this is central metal atom. Let the oxidation state of the central metal atom is X plus -1 plus 2 into 0 plus 1 into 0 is equal to +2. That means X is equal to 2 plus 1, that means +3. Here the central metal atom cobalt is in +3 oxidation state. Cobalt 3 plus has 3d6 electronic configuration in its valence shell. So the electronic configuration of its valence shell becomes like this. When the incoming ligands comes to cobalt 3 plus, then the 3d orbitals electrons are rearranged to accommodate the incoming ligands, like this. This electron comes to this orbital, and this electron comes to this orbital, and all the electrons here becomes in paired form. These two orbitals remains vacant or becomes vacant to accommodate the incoming ligands, right? Among the 6 ligands, 2 ligands donate its lone pair of electron to the 3d orbitals, 1 ligand donates its lone pair of electron to 4s orbital, and the remaining 3 ligands donate its lone pair of electrons to the 4p orbital, to the 4p orbital. So the hybridization becomes sp3d2. When the central metal atom is sp3d2 hybridized, then the structure or shape of the complex compound becomes octahedral. And it looks like this, where at the center of this square, cobalt remains, and above the plane, there is one ligand, below the plane, another ligand, and 2En or ethylene diamine remains at the four corners of the square plane, right? This bond is coordinate bond. The bond between NH3 and cobalt is coordinate, and this bond also are coordinate because these bonds are formed by the donation of the lone pair of electrons on the nitrogen atoms to the central metal atom, and overall charge is +2. So this is octahedral geometry. I hope you all have understood properly. If you have any doubt, please mention that in my comment box. I'll try to answer all the questions. Thank you so much for watching.